Hello, we are the International Space Station, or ISS, servicing robot Capstone team, and this is our final presentation. Our interdisciplinary group is made up of team members Lamia Farah, Daniel Fisher, Samantha Glassner, William Spencer, and Erica Trainey. Our problem statement is to design, build, and test an autonomous robot for the International Space Station, or ISS, that will drive along the walls of the ISS, avoiding obstacles and navigating the station to perform an example servicing task of cleaning blue handrails, alleviating astronaut time for more scientific experimentation. First, we'll discuss the need for our project. The International Space Station is a unique microgravity laboratory that has been inhabited since November of 2000. It has astronauts living on it 24/7 from a multitude of countries. These astronauts spend their time performing scientific experimentation. Here you can see the layout of the ISS is comprised of modules connected together. Astronauts use these modules for many different things. So they live there and they work there. So they have dinner there, they go have their bedrooms, they exercise, they go to the bathroom, and therefore they have to clean it regularly. These cleaning tasks involve about 2 to 4 hours of things such as cleaning handrails, wiping down communication panels, vacuuming, and we did a calculation for how much an astronaut's time is worth and found that it is about $110,000 per hour. Our team decided to have our servicing robot take on the task of cleaning handrails because we found that the handrails have a very known size, color, shape, and location inside the International Space Station. So looking at pictures that are found on Google Earth of the ISS, we can find that we know where the handrails are and we know the surfaces that they're around. So we can very clearly scope the project of cleaning these handrails with our robot.
To begin tackling our problem statement, we first looked into some pre-existing designs. When doing research, we focused on 3 different areas. The robot vehicle, which includes how our robot will move and adhere to the walls of the ISS in zero gravity. The cleaning mechanism, which indicates how our robot will autonomously clean each handrail. And navigation, how our robot will identify handrails, avoid obstacles, and know where it is within the ISS. For the vehicle body, we looked into wheeled and legged robot designs for our locomotion technique. And to say adhere to the walls of the ISS, we examined using vacuum pumps, a pinching method, and a drone fan method. For navigation, we looked into using 3D LiDAR cameras, infrared sensors, and 2D RGB cameras. For the cleaning mechanism, we examined using a passive arm and a rail runner method. The CAD for our final design is shown below. Ultimately, for the vehicle body, we decided to use wheels with tank-like drive and a drone propeller to keep the robot adhered to the walls of the ISS. For the cleaning mechanism, we decided on a passive arm that housed a soft robot that, when deployed, released fluid via a linear actuator and vibrated on the handrail like an electric toothbrush. For navigation, we decided to use a 2D camera for detecting handrails, infrared distance sensors for avoiding obstacles, and a LiDAR to achieve localization, all of which were connected to a Raspberry Pi.
Now we're going to get into some of the analysis we did to come up with our design. To get a better understanding of the vehicle's size and shape, we first analyzed the vehicle wheel size, wheelbase, and ground clearance using simple geometric relationships such as the breakover angle, the approach departure angle, and the maximum curb height. The breakover angle and curb height are important for considering wheel size and ground clearance, and since we expect to drive over obstacles and curbs as tall as 3.5 inches high, we determined that our vehicle needs to have at least an 8-inch diameter wheel. This analysis also showed that our wheels must be the furthest forward object on our vehicle to accommodate wall changes. Another aspect of the vehicle we chose to analyze was its ability to move from one wall of the space station to another. This is what we call maneuvering an internal corner or changing planes. In this maneuver, the vehicle must gain sufficient traction on its front tire to move to the second wall. Using this simple free body diagram, we came up with an equation relating the front tire traction to drone motor downforce. After analyzing the traction force at angles of theta between 0 and 90, meaning the vehicle is moving up the wall, we are concerned that the downforce of the motor will overcome the traction of the front tire, pulling the vehicle back down to wall 1. To address this concern, we decided to analyze a similar situation in which we angle the drone motor to our advantage. In this diagram, the drone motor is forward biased, helping gain more traction on the front tire to complete the plane change. This analysis was promising, and we planned to incorporate it into our design after we built the initial prototype. Here are the main driving components we chose for the vehicle. A LiPo battery powers a motor controller, which is used to control the driving gear motors. The drone motor has a separate battery than the drive motors, and is controlled by this electronic speed controller. We would have used a typical servo, like the one shown in the bottom image, had we ended up wanting to angle the direction of the downforce. When first designing our prototype, we had to plan for how we would end up testing the vehicle. In the diagram, the large light blue rectangle is a wall, and the vehicle has been turned onto its side. The small blue rectangle on the bottom is an air puck, which shoots a stream of air downwards to gravity offload whatever is sitting on top. This would allow us to test maneuvers such as internal corners, driving over obstacles, and our cleaning protocol to ensure these functions could be performed without losing contact with the wall. Due to the global situation we are currently facing, campus closed early, which affected some of our plans for building and testing our project. Though we were unable to perform this testing off campus because it necessitates the use of compressed air, the team found other ways to construct and validate the design, which we will talk about later on in this presentation.
Originally, we considered a more complicated robotic arm to deploy the cleaning mechanism like on the Boston Dynamics Spot. We proceeded with a 1 degree of freedom arm similar to a trash truck to minimize complexity. In order to decide on the most effective cleaning mechanism, the mechanical team ran potential designs through a trade study. To start, subsystems were assessed for criteria such as cleaning and mechanical and electrical complexity. For example, our baseline and alternate methods of gripping handrails were mechanical jaws and a soft robot inflatable. Factors such as the number of moving parts and the team's skill set made an impact on their score. We used our best engineering judgment to rank those criteria in order of importance to the mission. We were then able to quantify the effectiveness of each subsystem and down-select. We've decided on a soft robot that can inflate to grab handrails. A dry cleanroom wipe is installed on the white clips. Once the mechanism is secured on a handrail, embedded vibe motors similar to what's found in your cell phone provide mechanical cleaning like an electric toothbrush. And perforated tubing brings cleaning solution to the wipe. Our trade study identified an issue with disinfectant wipes drying out too fast, and designs to pull fresh wipes from a canister and clean all sides of the handrail scored poorly. Here's what the soft robot looks like inflated unconstrained. If it were inside of its housing, it would constrict inwards on a handrail. Fluid is dispensed with a custom syringe pump mechanism powered by a compact linear actuator. The soft robot is inflated with a pneumatic system comprised of a 12-volt vacuum pump and a solenoid valve. The trash truck arm is lowered with 2 servo motors, and mechanical vibration for cleaning is created by vibe motors.
To tackle our navigation analysis, we first examined what requirements the robot must satisfy to operate autonomously. These included detecting handrails, navigating to handrails while avoiding obstacles, changing planes, deploying the cleaning arm, and keeping track of its position in space.
The first major software hurdle was identifying these blue handrails. Here, we have outlined the process of identifying handrails in an image. Pre-processing takes the raw image and returns a binary one, with blue shapes being white and everything else being black. The detection step groups nearby pixels and encloses them in bounding rectangles for later analysis. Many of these bounding rectangles will be duplicates or unlikely detections, so these errors are suppressed in the filtering step. Here we have the actual output of this algorithm. The red bounding rectangle is then stored and passed on to the rest of the application.
To avoid obstacles, we purchased 2 different types of sensors. The first was a passive infrared motion sensor, which detects moving obstacles, such as astronauts, and the second was an infrared time of flight sensor to detect static obstacles. To localize the robot, we decided to use a simultaneous and localization and mapping methodology, otherwise known as SLAM. There exist several different open source algorithms for SLAM, but ultimately we decided on using Breezy SLAM, as the code was lightweight, the LiDAR was relatively cheap, and it was the easiest to integrate into the code base we created. The left image shows a sample output of a robot localizing itself in its surroundings using the Breezy Slam method. The right shows the 360-degree laser scanning LiDAR we purchased to implement Breezy Slam. To organize our code, we first developed a state diagram. The state diagram describes the state the robot will be in at each moment and what algorithms it will be implementing. So the robot will first start in the searching for handrail state. While it's searching for handrails, it'll be avoiding obstacles using SLAM and trying to detect handrails. Once it's found a handrail, it will begin navigating to the handrail using a navigation algorithm that we will develop, and all while avoiding obstacles and using SLAM. Once it comes within cleaning distance of the handrail, we will deploy the cleaning arm. We'll position the arm along the handrail to completely clean the handrail, and we'll retract the arm when cleaning is finished. If there are more handrails to clean on the current plane, then we'll go back to searching for handrails. Otherwise, if we cleaned all the handrails on the current plane, we'll move to the next plane. Moving to the next plane involves finding the plane edge while avoiding obstacles and using SLAM, and adjusting the wall grip so that way we can move to the next plane once we've arrived to it.
To program this, we decided to use Python as a matter of convenience and to speed up development time. Additionally, we decided to handle image processing with OpenCV, an industry standard open source computer vision library. All development was done via SSH session on a Raspberry Pi 3. We also used the Raspberry Pi camera module. A touchscreen was fitted to the Raspberry Pi so that we could perform motion tests without it tethered to a laptop or monitor. Now that we've covered all of our designs, we're moving on to the steps we took towards producing them.
Sections of the soft robot are cast in molds containing any embedded features. Multiple sections can be bonded together with more silicone with an airtight seal. Silicone is made from a two-part mixture. It can be poured into the cavity of the mold and cures after 24 hours. We pull vacuum on the molds to ensure that no air bubbles exist in the walls. With some clever mold design, we can make more intricate parts.
To begin manufacturing the vehicle, we laser cut some sheets of acrylic with all the mounting holes for various components. On the right, you can see an example of some mounting parts that we designed that were 3D printed. The goal of creating parts using rapid manufacturing techniques such as laser cutting and 3D printing was to allow for quick design iteration during testing. With the same silicone we used in the soft robot, we were able to manufacture our own wheels. The wheel hub and mold were 3D printed, and the mold created cutouts that improved the flexibility of the wheel. On the right, you can see the pulleys mounted to the 3D printed hubs with the timing belt in between them.
You can see here this is a final electronics board where we brought together all the electronics for the different parts of the vehicle. So we have the two motors that drive the vehicle and it's their motor controller. We have all the cleaning mechanism electronics, which includes a linear actuator to push the syringe, a vacuum pump to inflate the soft robot, and a solenoid valve to basically hold in the air of the soft robot when it's inflated. We also have all of the wall adhesion electronics, which includes a drone motor and propeller, which is controlled by an electronic speed controller. Finally, what is controlling the whole thing is a Raspberry Pi, which is in the navigation electronics section. And we also have some sensors there, including a motion sensor and a camera to detect handrails.
Throughout the spring, the electronics and software team were working together on developing the robot's ability to navigate its surroundings. Before group work was halted, the team was able to construct a control architecture for the code base, develop and verify the handrail detection algorithm, and begin implementing SLAM and the code to control the wheels. However, most of these tasks were not fully realized. Since we have not been able to work in a group, we have focused our efforts on displaying in a simulation what our path planning algorithm would have looked like. This diagram shows the navigation control architecture we created. This control architecture will implement the state diagram previously shown. The main controller class interacts with three larger classes: the map interface, the handrail locator, and the hardware controller. The map interface will house the SLAM implementation as well as the obstacle avoidance algorithm. The handrail locator consists of the handrail detection and ranging algorithms. The hardware controller interfaces with all exterior hardware that give feedback to the robot as well as help the robot complete its tasks.
In order to navigate toward handrails, We need to estimate their position relative to the robot and its camera. This is done by comparing real-time handrail detections with detections from a bank of calibration images. These calibration images are gathered using our robot's camera setup and our own mock handrail at various known distances. This animation illustrates the path planning strategy that would be employed by the robot. First, it orients itself perpendicular to the handrail, then it approaches the handrail and applies the cleaning mechanism. For long handrails, like the one at the top of the animation, the robot will clean the handrail in discrete steps, reapplying the cleaning mechanism each time.
Due to campus shutting down for COVID-19, we had to do our final prototyping at home. But you can see we were still able to create a basic prototype of our robot on the right. Looking more closely at the robot, the top level has the drone motor and the propeller. It also has the main controller, the Raspberry Pi, and sensors like the camera and the LiDAR sensor. The middle plate houses the battery packs, and it houses all of the system needed for the cleaning mechanism. So it has the pump and the solenoid valve to inflate the cleaning mechanism. And then if you look on the bottom plate, we actually have the cleaning mechanism syringe and linear actuator control the syringe, which is for the fluid part of the cleaning mechanism. And additionally, we have the RoboClaw and the two Pololu motors, which actually drive the tank wheels. Now you can see that we actually performed a driving test. If we were to do more development, we would play with the wheels and the casting process to make them a little more rigid so they wouldn't be as wonky as they are right now. And finally, we also did drone motor testing. So this is what would be used to keep the robot against the wall in the ISS, and we found those fully operational.
Now we're going to get into some of the project's management details. In order to stay on track with this project, a requirements tree was constructed. There are branches for autonomy, cleaning, navigation, and functional requirements. The requirements become more and more specific the further down the branch. They were written as specific as possible, with no bias to one specific design solution. We have a few examples to showcase how we qualify to our requirements. Let's start with acoustic analysis. The robot is held to the walls with a fan, which is the loudest component. It is important to adhere to ISS environmental requirements for noise. It is imperative for us to compare the noise created by the robot to the noise criteria curve specified in the ISS requirements document. We recorded the fan running at steady state and performed a fast Fourier transform in Audacity. We also recorded the sound pressure level with the Phonometer app to appropriately scale the recording after the fact. The FFT spectrum was discretized to its 10 highest contributions. We found that we adhered to the daytime noise requirements and almost make the nighttime as well. We plan to only use the robot during daytime, so this is satisfactory. We also devised a test to quantify the effectiveness of our cleaning method. While the routine contaminants that we will encounter, skin particles, finger oils, and germs, are all invisible to the human eye, we can contaminate a handrail with fluorescent analogs and count the number of white pixels under black light. Unfortunately, campus closed before we were able to conduct this test, so we've manufactured data to show how it works. Contaminated handrails would be cleaned both by hand and by the robot, and a comparison of the percentage of white pixels left would signify the winner.
Since we were unable to test out the robot using the gravity offloading air puck previously described, we created animations to show the motion of the robot. This slide shows the robot approaching a handrail and deploying the cleaning mechanism. This animation could be used to verify the distance the robot needs to be from the handrail in order to correctly deploy the cleaning mechanism. Here is an animation of the robot performing the plane change maneuver. As you can see, the cleaning mechanism would be in its retracted state for this maneuver. Though this simulation verifies that the footprint of the robot would be able to complete this maneuver, testing with the physical prototype would have allowed for a better understanding of the impact of the drone motor downforce and its effect in this critical part of the robot motion. The air puck we are going to use for testing has a recommended mass range. Summing the mass of the components on the robot and estimating the total mass of hardware needed, the robot would be below the recommended weight for the house air pressure of 60 psi on a smooth testing surface. This shows that we would need to add ballast to the robot for proper stability.
Here we have our evaluation of the handrail detection algorithm. Handrails were placed at various distances listed along the x-axis in two different orientations shown here in red and yellow. We then executed the entire handrail locator module several times for each test case and averaged the distance estimations that we found. While this data showed promising accuracy, given the analysis that we've done, these are the features of the project that could be improved moving forward.